everyone. Today in this session we're going to talk about the families of error control coding techniques, which are very fundamentals and applicable actually in practice, and are really interesting to consider because they are famous in also theory of coding. Okay, in generally error control coding are subdivided by three groups of families. Actually, the first is called linear block codes, and the second one called convolutional codes, and the third one is combinational code. Okay, the first one actually is the linear block codes. But what does it mean? The idea is really simple. The idea is that you have your actually block of encoder. So it's, for example, block of your encoder. Here it's your encoder actually. And then what you do is that you actually put a block, because its name is block. It's actually a block which length, for example, k bits, so k bits of, for example, 1 and 0 here. And then what you're gonna do is that you enter this stream to your encoder, and it gives you some block also which contains of n bits instead of actually k bits. So and with this case that n is larger than k, so actually in this case you add some redundancies, like all of the actually error control coding techniques, that we add some bits to the input stream, just to have an ability to control the error that may occur in receiver, for example. So now here the idea of this family is really simple. The idea is just to have a linear combination of these k bits, and to get, for example, a 1 bit here in the output. So the idea is exactly this, to have a actually to calculate, for example, ith of binary bits that I have in output. What can I do? I can choose some combinations of these k bits, and then by combining these elements, I can achieve and can obtain the result ith actually bits elements that I have in my vector and of n bits. So it's actually the idea of linear block codes. So basically it's just a linear combination of your k bits inputs. Okay, now let's consider a little bit about the existence, actually family that exists in practice. Okay, there are a lot of actually propositions, and there are a lot of kind of application coding that we can apply, but the famous one, or the first we can call a really famous coding, which is actually repetition codes. And repetition, but what does it mean? The repetition is, the idea is really simple. For example, you want to send, imagine you want to send, for example, yes and or no. Actually, you want to send the symbol yes or no. So you can just code it by 1 and 0, isn't it? Okay, now I want to actually add some extra bits just to do my encoder and just to control this symbol. The idea of repetition is just to actually says that you can just repeat your data exactly the same. It means that you can, for example, repeat the bit 1 3 times. So I repeat it 3 times, and you can repeat, for example, 0 3 times. So I will have actually this stream that it's actually the real stream that I'm gonna send through the channel. And so imagine that you can, for example, obtain in receiver 1011. So you can tell that it's actually more it's more similar to, for example, yes, it's more actually similar to 1111, and then it will be, you can actually have an ability to correct these bits to 1. So it's the idea of this method. Okay, it was actually the repetition method and the repetition coding. The second one is called, which is also very famous by a mathematician of coding techniques, Hamming codes. For example, we can imagine that we can have a Hamming of 7, 4, and 3. Okay, it's really simple. So when you have actually your combinations, for example, when you have an output actually, and this output is just a linear combination of k bits of your inputs, so it means that in basically, or in other hand, or in other saying, in generally speaking, actually it's just a matrix. So this block is just a binary matrix that you multiply it by the inputs. So it's basically a matrix. So this block is a matrix that you multiply your k-bit stream to obtain your output. So for example, for this kind of code for 743, the matrix of your encoder will be this, in this form actually. Okay, as you can see here, we have actually 4 lines, we have 4 rows actually, and we have 7 columns, and we have just 4 rows. So basically you multiply your k bits, which is in this case actually k is equal to 4, n is equal to 7. So basically you multiply your k bits, and you multiply, you just make your inner product in global field of 2. So in binary mode, you just multiply your 4-bit stream to this matrix, and you're gonna obtain the results, and the 7 bits, the vector contains 7 bits of your stream. So it's basically the idea of Hamming codes. We can actually generalize also this code mathematically through a relative combinations of powered of 2, but it's not really interesting in this case. I just want to introduce a little bit about the very famous, so I will go very fast. Okay, the fourth one is called, which is also very famous, is called actually Reed-Muller. Reed-Muller code is also a very famous codes which are introduced in this case, and also a very also fundamental code, and very powerful actually codes in linear block codes are called LDPC, or actually linear or low density parity check. So basically what you have here, you just have a matrix with a parity check, or with a matrix, and the actually appearance of this family of coding of error control codes are to have low density parity equals to 1. So basically, for example, you have a, I don't know, you have a, for example, 1000 multiplied by, I don't know, for example 1500. For example, imagine that you have this byte, you have this actually bits stored in your matrix, and actually there are just the resist actually the resist just, for example, 1.10 actually 01 of your data of these elements are gonna be equal to 1. So the idea is that just 1% of your registered data on your matrix is equal to 1. So the rest is actually 0. So it means that your matrix is low density. So there is no a lot of 1 on your matrices. So it's the idea of low density parity check, which are very strong in terms of performance and in terms of coding techniques. So it's really interesting to consider also. Okay, now the fifth actually family of codes are called, which is also very famous, are called actually polar codes. These codes are recently published, or when I say recently, it means that after 2000. So it's really a codes which can attain to the Shannon limits. So they can attain to Shannon limits, and they are basically very useful and practical to implement and to use in practice. LDPC are also very close to the limits of Shannon, but polar codes can attain just this limit of Shannon in information theory actually. So these are the very famous block codes that we have. But there is also some another actually subdivision or some family of linear block codes which are very important, whose name is cyclic codes. So basically, cyclic codes is very important codes. But why? What is the actual idea of cyclic codes? The idea of cyclic codes is that, okay, your matrix here, which is actually that actually we were talking about it later, earlier, is just a matrix. So we call it, for example, a matrix. So your encoder is just a matrix in which you have some bits 1 0 etc 1 0 etc. So you have just 1 0 etc, and for example it's k by 1. Okay, so you multiply just your k bits by this matrix and you're gonna have your n bits coded message. But the idea of cyclic code is that, imagine that your matrix has a good advantage of storing data. What does it mean is that, imagine that if you know, for example, the first row, you know just the first row, and by knowing just the first row or each row of your matrix, you can actually create your all matrix, your all data, your all actually matrix chi by n. For example, imagine that we can construct it by this actually idea that, for example, I imagine that I will have, for example, 1 0 0 1, and then what can I do for second line is gonna be to have a shift. Just I will shift this bit, for example, to the right, and I will create my second actually a line of my matrix. So it's gonna be, for example, something like that. Isn't it? So I shifted by in cyclic manner to the right, and I will have, so 1 is gonna be there, 0 is gonna be there, 0 is gonna be there, and 1 is gonna be returned to the first actually elements. So the second line is gonna be something like that, and for the third is gonna be something like that, and the fourth is gonna be something like that. So actually now you created your matrix which is corresponding to your what is your interest. So this method is very important, and these codes actually are gonna be very important, because as soon as you do that, and as soon as you did it, in terms of implementation is very important, because if you know, for example, the first line, you can immediately create your matrix, and then you can obtain all of your matrix that is interested for you. This actually idea is used, and we call it effectively cyclic code. The reason that we call it cyclic, because you can just shift your bit stream, your bit actually row in a cyclic manner to obtain the other rows or the other lines. So it's the idea of cyclic code. So basically what I need is just a, for example, some vector, or the first, for example, imagine the first vector, which is, for example, which could be, for example, something like that. So if I know, for example, what I called it, for example, G is equal to something like that. If I know G, I know actually all of my matrix. So this matrix is known for me. So these codes are called actually cyclic codes, which are very useful in practice. There is a very famous, there are actually a lot of codes subdivided in this way. Okay, the first codes, or the first cyclic codes, which is obtained by this family of group codes, is called Golay codes. So Golay codes, for example, Golay of 23, 12, and 7 is very famous. Well, what does it mean? Actually, this number is not really important right now. What is important is just I want to just introduce some names and nothing else. Okay, so the Golay codes also is very important, which are basically a cyclic codes. These are actually the family of cyclic codes, a subfamily actually of cyclic codes. The other very important codes are called CRC, or cyclic redundancy. Cyclic redundancy. So cyclic redundancy codes. Basically, the idea of CRCs is not just to, actually is just to detect the error that exists. As you can see by its name, it's cyclic redundancy codes. It means that you just add some redundancies by some configuration cyclic in a cyclic manner. So it means that you just have a redundancies which are not in a priori, which are not capable, and or which has not the ability of just correcting the errors, but they can, and they would be used just for detecting the error, and they're actually very useful in some applications like wireless sensor networks, like, for example, actually there are a lot of like the system of mobile GSM, or the other actually generation of system. So they're really interesting, and also they are very interesting, and they're very applicable in such, in, for example, in DVD, or some actually storage actually boxes that you want to use, and you want to actually store some data. So they're very useful, just to knowing that. For example, there is in the form of CRC 16, CRC 32, etc. So they are really the interesting problem. There are also another very famous of cyclic codes, which are actually whose name is Ritz-Solomon, or RS codes, which how we call it is something like that. RS codes are really are very actually famous codes. That also it has a subdivision which we call it actually BCH codes. So BCH codes is just a special case of Ritz-Solomon codes. But what does it mean actually? The idea of Ritz-Solomon codes is just to have and to play with some roots of this actually G. What does it mean is that, okay, we can actually polynomialize this G. It means that you can write it in this way and in this manner. You can just write it in this manner that, okay, you can actually weight, you can weight for example the first bit by 1, the second by x, the third by x2, x3, and x4. So it's gonna be, the g of x is gonna be x4 plus x, as you can see, the inner production of these two curves in these two vectors is gonna be gx equals x to the 4 plus x. So it's the polynomial of this, for example, code. So basically it's gonna be a very mathematical problem right now, is that to just find the roots, actually the roots of this polynomial. So to find out and to actually organize these roots, what we do is we can actually manage these roots by the way that we can obtain, for example, a relationship between the roots of this actually polynomial, to obtain a very intelligent or very strong code for a kind of, for example, Ritz-Solomon or BCH or something like that. So the idea here is just to play with polynomials, so, and basically with actually roots of polynomials, So basically it's a more or less it's just a actually algebraic mathematics here. It's really algebraic. It's actually algebraic math, and you must actually have to do some algebraic mathematics here to obtain your actually polynomial, your generator polynomial, which is actually your gx. Is actually how we call it, generator. It's actually what does it mean actually? G is actually generator of your matrix or your code. So basically it's actually the idea of this kind of error control coding techniques. And BCH is just to have a special case of this root. So basically whenever you have some root from your, for example, field that you have created, so you can obtain your some, for example, roots which are corresponding to Ritz-Solomon, and when they are in one by one beside the other, is going to be BCH. How we call it is actually BCH. Okay, now we actually finished the part of linear block code. I'm gonna talk about now about a little bit about the actually convolutional codes. Okay, let's just have a really quick cleaning here, and we're gonna start as soon as possible the part of convolutional. Okay, the idea for convolutional code is just to say that here actually what you have is you have a combination linear, you have a linear combination of your k bits, and to obtain actually your output for ith elements or ith entry of your vector. But what is here the difference here exists is that, okay, here you have also your encoder, so it's actually your encoder. You put also, for example, k bits here also, so it doesn't matter, so it's actually the same. and it can obtain, for example, n bits in output. But what is the difference? And here, imagine that you interact with your k bits and you're gonna obtain your n bits in output. The idea here is just to have some effect and some registered actually data. It means that you have here some memories, which are very important memories, just to obtain or just to register your data in such a manner in some clocks, let's say, to calculate the ith of your bits. So it means that basically in addition of a combination of k bits, you're gonna have some effect from the previous k actually bits. If, for example, imagine that it's your time t, instance t, and it's for instance t minus 1. So basically you have some bits here. So basically what you obtain in the, for example, in this time actually, is not just the linear combination of these guys, and in plus of this, it's a combination maybe or the effect of the previous t minus 1 data in the previous actually slide or window or vector of k bits. Why? Because there exists some flip-flops, there exists some actually memories that contains that actually register your data, and they can, for example, give you the bits. For example, I don't know, in 10 clocks after, or it depends actually the number of flip-flops that exist in this block. But for example, you can obtain, you can actually see the effect of this previous window k bits window. So it's just the idea of this. While here you didn't have actually memory, so it was actually basically memoryless. So the linear block codes are basically memoryless codes. So it's actually the idea of convolutional code. It's how we call it, convolutional code, because actually it's just something like convolution, to take a convolution of your bit stream with a filter, actually in a two binary field. It's actually a filter that you apply on your data. So it's not just a matrix. It's so it's gonna have a actually machine state or state machine. So you're gonna have some state machine here, and this state machine actually tells you that what is the output. So this state machine tells the state of your system and the state of your data. So you have some parameter called, for example, m, and this parameter is controlled by, for example, the designer of this actually hardware or something like that. And they're really very important and very practical in terms of applications. There are a lot of applications that use actually convolutional codes as a very famous and powerful codes in practice. The third one is combinational codes. The combinational codes is the idea is very simple. The idea is just to add and just to combine, for example, some linear or convolutional codes with actually modulation. What does that mean is that actually the engineers of communication, they actually the guys who work on these topics, they decided actually once a time they decided to optimize to have a actually once and at the same regard on these topics. It means that they wanted to optimize to have a better performance by regarding codes plus modulation in one time. So it was the idea of designing, for example, there exists some convolutional plus, for example, a very famous modulation BPSK, or maybe 8 QPSK or QPSK, etc. So there are a lot of propositions here that are really interesting to consider. Okay, I think that it's good for this session. Just to have a brief introduction on some families of error control coding and some ideas. Maybe in the future in the future videos, we're gonna talk about some. We'll talk about the encoding and decoding techniques that we used for these families of codings. Thank you so much. See you soon.